questions on the homework so far? I've seen homeworks from a few people and they look good. And it's not due until Wednesday, but you know, hopefully you're working on it sooner rather than later. Yeah.
Can we turn it in?
If you're willing to take the chance that I might lose it, sure.
Oh yeah, I've got a picture of mine. I'm turning it in.
Really? I'll take it.
Where is it?
Do we get extra credit if you lose it?
No, but you'll get a good story from me.
It actually it makes your grade better because if you get a 0 on it because he loses it, it makes you work harder.
Oh, true.
That's true. So I should just throw these out when I leave.
Yeah.
All right. So we were talking about quantifiers, and we did the universal quantifier and the existential quantifier, and I want to talk just a little bit more about those, and then we're going to talk about rules of inference, which is really the sort of heart of the matter. But some other things to think about. For all x, p of x and q of x. And there's a universe specified, and p and q are propositions over x and so on and so forth. But for all x, the statement p of x and q of x, to say that that is true means that for any x that you pick, p is true and q is true, right? All right, what about this? For all x, p of x, and for all x, q of x. Are those two logically the same?
Yeah.
It's a little tricky to think about, but yeah, those are exactly the same thing. The first one's saying for any x that you can think of, p will be true and q will be true. The second one says for any x that you think of, p of x will be true, and for any x you think of, q of x will be true. So these are logically equivalent. I'm missing your closing parentheses. Okay, how about if we do the existential quantifier? There exists an x such that p of x and q of x. Or there exists an x such that p of x and there exists an x such that q of x. Are those logically equivalent? Can you think of propositions that would show that these are not equivalent? Because in fact they're not logically equivalent. So showing things are identical is hard because you have to show that they're identical for all possible situations. But to show that something is false or that two things are not identical, you only need one counterexample. Sometimes that's easier. So what could be a counterexample here? Can anybody think of propositions p and q which show that these are not the same thing?
P of x is even, q of x is odd. That works.
P of x is the proposition x is even, q of x is the proposition x of odd. Does there exist an x such that x is even and x is odd? No. Does there exist an x such that x is even? Yes. Does there exist an x such that x is odd? Yes. So both of these are true, their conjunction is true. So the right-hand side is true, the left-hand side is false. So those are not logically equivalent. How about these? Kind of feels probably equivalent, right? So these don't always work the way you might think at first. And we played with negation. Right, saying there does not exist in X such that P of X is the same as saying for all X, not P of X. This says for all X, P is false. This says there does not exist in X for which P is true. So those are equivalent. All right, and we can nest quantifiers. So we can say things like for all X there exists a Y, or for there exists an X such that for all Y. So for all X there exists a Y such that X plus Y equals 0. And we're working over integers today. So for all X there exists a Y such that X plus Y equals 0. Does that seem true or false?
True.
That seems true. How many people think it's true? It's true. Democracy wins out. So we can think of this as, for example, let P of X be the proposition. There exists a Y such that X plus Y equals 0. This is a proposition about X. Give me an X, this proposition says there is some Y such that X plus Y equals 0. And in fact there is. I can set Y equal to negative X. So P of X is always true. And this statement here can be rewritten as just for all X, P of X. So when you try to analyze these, you can break them down into sub-propositions and sometimes think about them more easily. There exists a Y such that for all X, X plus Y equals 0. So this first one was true. What about this statement? There exists a Y such that for all X, X plus Y equals 0. So I'm just rewriting this as there exists a Y such that P of Y, where P of Y is the proposition for all X, X plus Y equals 0. So let's look at some particular propositions. P of 0 is the proposition for all X, X plus 0 equals 0. Is that true or false? That's clearly false, because if X is 1, it fails to be true. P of 10 is the proposition for all X, X plus 10 equals 0. That's true for one X, but it's definitely not true for all X. P of negative 20 is the proposition for all X, X minus 20 equals 0. I mean, that's just saying for all X, X equals 20, and that's clearly false. And any value I plug into here, I can repeat this argument and show that that proposition is false. So in fact, P of everything is false. So does there exist a Y such that P of Y is true? No. So this is actually false. So the order in which you nest these things definitely can make a difference. Now, it could be that this and that are both true or both false. They're not necessarily negations of one another. And we can nest the same quantifier. For all x, for all y, x times y equals y times x. Well, that's true. For any value of x you pick and any value of y you pick, this is true. That's just a formal propositional logic way of stating commutativity. For all x, for all y, x is bigger than y, that's obviously false. I can pick x equal to 0, I can pick y equal to 1,000,000, and that's false. There exists an x, and there exists an y, such that there exists a y, such that x times y equals yx. That's also going to be true. And in a sense, if it's true for every x and y, then there certainly exists an x and a y for which this is true. But the existence is, in some way, feels weaker. There exists an x such that there exists a y such that x is bigger than y. Well, that's true. X is 10, y is 0. So this is equivalent to true. So there's no handy rules that I know of for looking at these nested quantifiers and knowing how they relate to one another. You really kind of have to look at each of them in detail. All right, so I'm going to pass around a two-sided purple sheet for you to keep and frame on your wall or tattoo or whatever it is you want to do with it. This has the laws of logic from page 58 of the book, commutativity, associativity, distribution, De Morgan's, all of that stuff we've already talked about. The other side, 59, has these common implications and equivalences. These are the things we're going to start talking about right now. These are sometimes called rules of inference, and they're the logical rules we can use when we construct a proof to move from one line of the proof to the next. And they have fancy names like conjunctive simplification and biconditional equivalence and things like that, so they're fun to talk about, especially with people who haven't had 215. And we're going to be talking about proofs and ways to prove that certain things follow from other things. And let me give you an example of something we can prove. If it's sunny, then I am outside running. It is sunny, therefore I am outside running. So I have three statements here. I'm going to number them 1, 2, 3. Is each of these statements a proposition? Which one's not a proposition? Okay, let me get rid of the word therefore.
Number 1.
Okay, so ignoring the word therefore. If it's sunny, then I'm outside running. It is sunny, I'm outside running. Those are all propositions, right?
Yeah.
They're declarative statements. Do we know if statement 1 is true or false? It would be kind of creepy if you knew that. Because, you know, there's a lot of sunny days, especially in summer. The days are long, and maybe I go outside running when it's sunny, maybe I don't. Right? So we don't really know if statement 1 is true or false. Do we know if it's sunny? Well, I can look out the window and I know it's not sunny. But you know, maybe we're in a room with no windows. Or maybe we've got our eyes closed. Or something is going on. And we may not know if statement 2 is true or not. And I am outside running. Well, it's pretty clear right now I'm not. But if you come back and you do this an hour or two from now, I could be outside running, I might not be outside running. You don't really know. So it may be completely impossible to know whether any of these statements are true or false. There's nothing we can learn in this class that's going to let us prove that 1, 2, or 3 are true or false. Okay, this is not a course in my habits or my daily life. But we can prove one thing. What we can prove is the following. If 1 and 2 are true, then 3 is true. We can say we'll be able to say with absolute certainty after today, if statement 1 is true and statement 2 is true, then statement 3 is true. And that's kind of powerful. If it's true that if it's sunny, then I'm outside running, and if it's also true that it is sunny, you can guarantee I'm outside running. Now, why is it that 3 follows from 1 and 2? Well, that's a really good question. That's a fundamental question. That's the kind of question that Aristotle struggled with. If you know 1 and 2, how can we conclude 3? And I don't know if I have a good answer for that. But it's true. I have a cheap answer for it. The cheap answer is called detachment. Detachment, let me write it down more largely. P implies Q and P taken together implies Q. Okay, this is a way of saying the following. If P implies Q is true and P is true, then Q is true. So P implies Q is true. That's really what we mean when we write down P implies Q. Right? When we write something down, we're really talking about it being true. The and is this conjunction symbol. P is true, that's what P means. Then Q is true, that's just what the Q means. And this double arrow here is really just a fancy if-then statement. It's really saying if everything on the left, then the thing on the right. Right? But if we use a single arrow, we're not sure if we're saying P arrow Q and P arrow Q or so on and so forth. So it's a way to sort of say everything on the left implies the thing on the right. And we can think of it as if this and that, then this other thing. So if this was proposition P and proposition P and proposition Q, this would be the proposition if P then Q. So given if P then Q and given P, we can conclude Q. So this statement 3 follows from the first two statements because of this property called detachment. So let's develop a language for talking about these things. So our proofs will generally look like this. We write them vertically, and the idea is everything that we write down above this line is supposed to be true. And the line is kind of like a therefore. And we can read this proof as saying, given all of these things being true, we can conclude the thing below the line. If P implies Q is true, and if P is true, then Q is true. Now logically this makes sense to us, hopefully, right? Because this statement precisely says if P is true, then Q is true. And here we're being told P is true. And so from what we just got, Q must be true also. Do you hear that?
What was that?
I don't know, but that was high pitched. It was what?
My insulin pump.
Oh, was it?
Insulin pump?
Yeah?
Yeah, that.
Oh, okay.
Yeah, that's right.
That's okay.
Some sugar or whatever it was, I don't know.
Yeah.
I thought it was coming from outside. So if P is true, then Q is true, right? And here we're told P is true, so we just said if P is true, Q is true, so Q must be true. So this is logical, right? In the sense of Supertramp, maybe. It makes sense, right? And most of these are kind of the same thing. Let's look at the chain rule. P implies Q and Q implies R means P implies R. So let's start writing some of these down. So this is detachment. Sometimes this is called direct reasoning. All right, let's look at the chain rule. Suppose we're told if P, then Q, and we're told if Q, then R. We can conclude if P, then R. So if today is Friday, then we're in CSE 215. If we're in CSE 215, then I'm standing in the front of the room talking. So we can conclude if today is Friday, then I'm standing in front of the room talking. Those weren't quite true, but you know, you get the idea, right? And how do we know this is true? Because if P is true, we can conclude Q, and given Q, we can conclude R. So given P, we can conclude R. Okay, why is this useful? Prove that if A implies B and B implies C and C implies D and A is true, then D is true. Well, I can prove this pretty easily. I can say A implies B. I'm going to call this statement 1. Why is that true? I'm assuming it's true. It's part of my hypothesis, right? An if-then statement is if some hypothesis, then some conclusion. So A implies B, that's a hypothesis. Statement 2 says B implies C, that's also a hypothesis. Statement 3, I can use the chain rule, and I can say therefore A implies C, that's the chain rule, applied to statements 1 and 2. I also know that C implies D, that's a hypothesis. And I can use the chain rule again. A implies C, C implies D, therefore A implies D. That's the chain rule applied to 3 and 4. And I also know that A is true because that's another hypothesis. Well, I know that A implies D and A is true. What can I conclude? I can conclude that D is true. Why? Detachment. Using rules 5 and 6. And so I've proven in 7 steps that from these hypotheses, D is true. That's detachment.
No, that's on the opposite.
6, hypothesis. Yeah. Now we can prove things with truth tables. Right? I could make a truth table with A, B, C, and D and list all the possible values and show that in every situation, if this side is true, then the right side is true. 4 variables, how many rows do I have in my truth table? 250 question.
Scott, let us skip that part.
Wait, what?
No. Truth table with 4 variables.
Oh,
Okay, truth table with 2 variables. 2 to the 4th. So 16 rows. So 7 rows versus 16 rows. Suppose we do this with A implies B, B implies C, all the way up to Y implies Z, and A therefore Z. Well, we can do this in about 28 rows using propositional logic. Truth table is going to have 26 variables, 2 to the 26th rows. How big is 2 to the 26th? 64 million. So 2 to the 10th is about 1,000. Good rule of thumb to keep in mind. So 2 to the 20th is 1,000 squared, that's 1 million. Yeah,
No, I think I get it.
you got it?
Yeah.
Okay. So sometimes using these rules of inference will get us to an answer more quickly than a truth table. Now if we're a computer, we don't mind doing a truth table with 26 variables. It would take us a few seconds. Right? But as people, we're not good at that.
How big would the K-map be?
That would be bad. It's the dimensionality that would be a bummer, because you'd have to keep a really big hypercube. But computers don't care about K-maps. They'll just slog on it, get more liquid freon to cool down. All right, so let's look at some of these other rules of inference, and I'm going to pull it from the textbook because it's easier to read. All right, so detachment or direct reasoning says if P implies Q and P is true, then Q is true. This next one is interesting, indirect reasoning. So indirect reasoning says the following. Given that P implies Q and given not Q, we can conclude not P. So let P be the proposition I win the lottery. Man, I got spammed the other morning and it was filled with like 6 numbers, just repeating over and over and over again a few hundred times. This is it, man. I ran out, got my lottery ticket, didn't win. Okay, let P be the proposition I win the lottery. Let Q be the proposition I buy a new car. I love my car, though. I wouldn't do that. Maybe I'd buy a Tesla. So P is the proposition I win the lottery. Q is the proposition I buy a new car. And let's suppose if I win the lottery, then I will buy a new car. And let's suppose that's a true statement. And suppose I did not buy a new car. What can we conclude? I did not win the lottery, or I'm a liar. Right? We can conclude I did not win the lottery. That follows logically. So this is called indirect reasoning. Okay, it worked in this particular case. We could see those propositions and convince ourselves that the conclusion was true, but it works regardless of what the propositions P and Q are. That's the power of these rules of inference, right? It doesn't matter what the propositions are. As long as we know if P then Q and we know not Q, we can conclude absolutely not P. And it kind of makes sense. Because suppose that in fact P was true. Well, if P is true, and if we know that P implies Q, then Q would have to be true. But we've also been told Q is not true. Well, I can't have bought a new car and not have bought a new car, right? It's got to be Q or not Q. So the only possibility is P must be false. So that's indirect reasoning. And indirect reasoning is powerful. Okay, there's two things that look like rules of inference that actually do not work. They're actually called fallacies. The first one is this. P implies Q and Q, therefore P. That's a fallacy. It's not logically correct. If I win the lottery, then I buy a new car. I buy a new car, therefore I won the lottery. Well, I might have just decided to buy a car anyway. I may have won the lottery or I may not have. You cannot conclude P just from P implies Q and Q. So this is named the fallacy of affirming the conclusion. And the way I remember that is that what we're doing in this argument is we're stating that the conclusion is true. We're affirming the conclusion and then we're stating a fallacy. Okay, the other fallacy is this. P implies Q, not P, therefore not Q. And it's almost the same thing, right? If I win the lottery, then I buy a new car. I did not win the lottery, therefore I do not buy a new car. We don't know if that's true or not. So this is a fallacy of, in this case, we're denying the hypothesis. The hypothesis of this is P, and we're saying, let's suppose P is false. This is the fallacy of denying the hypothesis. So direct and indirect reasoning are logically sound, and those two fallacies are not. So there's direct reasoning. There's indirect reasoning. Those are correct, and these are your two fallacies. Okay, so let's look at more of these statements. Disjunctive addition. P implies P or Q. And there's no Q over here on the left. Apparently it doesn't matter what Q is. P implies P or Q. So let P be the proposition. I'm thinking of the number 25. Well, Q can be anything. Q could be the proposition that elephants can fly. And this says if I'm thinking of the number 25, then I'm thinking of the number 25 or elephants can fly. Is that a valid statement? Absolutely. Because if P is true, then this disjunction is true, even if Q is absurd. Not that flying elephants is absurd. Or it shouldn't be. So if P, then P or Q. Disjunctive addition, because we can OR other things onto P, and as long as P is true, the or with other stuff is still true. That's useful because sometimes adding more things to an expression lets us further simplify it down the road. Maybe we can factor something out, or maybe we can apply some sort of De Morgan's theorem or something. So disjunctive addition. Conjunctive simplification goes the other way. If P and Q is true, then we know P is true. Well, that kind of follows from the definition of conjunction. To say that P and Q is true means P is true, and it means Q is true. So if someone says P and Q, I can very confidently say P, and I can just as confidently say Q. All right, this one's interesting. Disjunctive simplification. P or Q and not P implies Q. Now we can prove all of these with truth tables, but truth tables don't always sort of enlighten conceptually what's going on. But think about this logically. P or Q tells us that either P is true or Q is true, or maybe both. Right? But it says at least one of these is true, P or Q. And if we're also told P is false, what can we conclude? Q's got to be true. Why? Because that left part says either P or Q is true. And if P is false, Q must be the one that's true. And similarly, if P or Q is true and Q is false, then P must be true. Chain rule we already talked about. Conditional equivalence we talked about the other day just from looking at the truth table. If P implies Q, then either P is false or Q is true. And that one, at least for me, doesn't have a really strong intuitive interpretation. But if you look at the truth table for implication, the thing on the right is exactly the 1101 pattern you see. And then biconditional equivalence we looked at the other day, and we said that it was basically an exclusive NOR, and this is the logical expression for exclusive NOR. P and Q are both true or both false. All right, and then contrapositive, we looked at these the first week. So P implies Q is logically equivalent to not Q implies not P. So if I win the lottery, then I will buy a new car. If I don't buy a new car, then I did not win the lottery. And don't think of cause and effect. Okay, these are not talking about cause and effect. These are statements with truth values. So if I win the lottery, then I bought a new car. If I did not buy a new car, then I did not win the lottery. It's not that if I refuse to buy a car, my lottery ticket will change to losing numbers. Okay? It's a relationship between the truth values. All right, well, let's start doing some proofs with these. And again, this is kind of a trial and error, thinking about these rules of inference and seeing what we can do with certain statements to try to turn it into something that that gets us to our conclusion. So let me give you a series of statements and a conclusion, and let's try to prove it. So here's an example. If you send me an email, then I will finish my homework. If you send me an email, then I will finish my homework. If you don't send me an email, then I'll go to sleep early. Yeah, I can relate to this.
Sounds like me talking to my mom.
If I go to sleep early,
I wouldn't talk to Ray in person, so.
then I'll wake up happy. Therefore, if I don't finish my homework, then I'll wake up happy. So you're trying to convince yourself you shouldn't do your homework so that you wake up happy. But you gotta wonder, is this logical reasoning? The first statement is true, because I'll forget to do my homework unless you email me. If I'm not staying up to do homework, I'm just gonna go to sleep. So the second statement's true, and if I go to sleep early, I'll probably wake up happy. That's true. So I'm concluding that if I don't do my homework, I'll wake up happy. Can we prove that? And we can argue it in our heads and probably come up with a proof, but the idea here is, can we construct a formal written proof that we could show to somebody who understands propositional logic? They could read it, nod their head, and say, yes, that is correct.
I mean, I have like 12 years of research backing that that's correct.
That's a good, yeah.
I think the only way to find out is if we have to test this.
So I can give you homework one day and email you to do it, and then the next day I won't.
Yeah, Danny, feel free to not do your homework.
So, and this is an interesting question because, finding a counterexample is totally something we can do. If we can find a particular instance where something is false, that's all we need to do. But to prove something is true, how many examples do we need? How many tests do we have to run? Really, all possible tests. This works for truth tables because truth tables, variables can only have a limited number of values. And even if you have 4 variables, there's only 16 possible combinations of values. We can do that. But to prove a theorem from algebra about integers, we would have to show it for every possible integer. I was wondering. And so being able to argue logically is sometimes more viable than trying to exhaustively show something. Okay, so let's make some propositions. So let P be the proposition. You send me an email. Let Q be the proposition. I finish my homework. Let R be the proposition. I go to sleep early. And let S be the proposition. I wake up happy. And being this is a written language, I'm being sloppy in here. Right? Technically, my proposition S should be I'll wake up happy. Right? And my proposition R should be I'll go to sleep early. Right? And I'm modifying these a little bit because this is more natural to the way I speak. But our first task is to translate from this form where we've got all these words and all this wiggle room to propositional logic, right? Something with P's and Q's and arrows and funny negation symbols. So to do that, first I'm going to define a series of propositions. Now, why did I pick these propositions? Well, I could have said, let P be the proposition. If you send me an email, then I will finish my homework. That's a valid proposition. And Q could be the second proposition and so on. But I'm trying to put these statements together And if I make my proposition smaller, there's more ways they can go together. So as a general rule, I'm going to try to make my propositions small statements. If there's an if-then, I'll make the hypothesis a proposition, I'll make the conclusion another proposition. And now I'll rewrite this first one as simply if P, then Q. Okay, so let's see if we can prove this conclusion. And I'll keep this nearby, but let's start rewriting. So if you send me an email, then I will finish my homework. Well, P says you send me an email, Q says I finish my homework. So our first statement is P implies Q. I'm going to label that 1. That's a hypothesis. Well, let me state what I'm trying to prove first. Statement 1 says if P, then Q. Statement 2 says if you don't send me an email, so how do we write that? Not P. Then I'll go to sleep early, that's R, so not P implies R. If I go to sleep early, that's R, then I'll wake up happy, that's S. The conclusion is if I don't finish my homework, so finish my homework is Q, so not Q, then I'll wake up happy, S. So this is the propositional logic version of this 4-line paragraph. And we want to prove that this is true. Okay, so at this point the propositions don't matter because again we have no idea if these propositions are true or false. It should not matter. We're trying to show regardless of their truth value, this line of reasoning is valid. So let's put down what we're trying to show. So I'm going to start by just stating if P then Q, that's a hypothesis. I'm just going to state all the hypotheses. All right, what can we do with these 3 statements we've written to come up with some new propositions? Is there anything we can do using things on our purple sheet maybe? And again, this is just kind of trial and error. It may not be something that looks like it's going to be useful, but let's just start making some changes.
Thinking, I don't know how much good it would do, but you could use conditional equivalence.
Okay.
Break them into or remove that.
Which one do you want to do it to?
I'm not sure.
Should we just go for the first one?
Do it all of them.
Okay, let's do conditional equivalence. Let's see where that gets us. So conditional equivalence says if P then Q is the same as not P or Q. So we could say not P or Q. This is conditional equivalence of 1. We could say not P. Well, I'm just going to say P. This is where I'm going to be a little skipping one step. P or R. That's conditional equivalence of 2. And not R or S. That's conditional equivalence of 3. Well, we got more things written, so we probably have a better chance of combining some things. What else do we see?
could use contrapositives.
Okay, what should we do contrapositive on? You want to do it on all of them?
That's all.
All right. We're getting paid per line of proof, so this is good stuff. So let's do the contrapositive of 1. Not Q implies not P. Not R implies P. And not S implies not R. Everything we've written is true. Right? These are true because they're hypotheses. And these are all true because they follow from these true statements. So we've got 9 things written that are true. Now what we're trying to show is not Q implies S. We can't write that down yet because we don't know that it's true. But we're trying to do something to these things that will get us to where we can show if not Q, then S.
You need chain rule for 2 and 3.
Chain rule 2 and 3, I like it. All right, 2 says if not P, then R. 3 says if R, then S. We can chain rule those and say if not P, then S. All right, what else? And we're looking for not Q implies S.
And then chain rule 7 with 10.
So 7 says not Q implies not P. 10 says not P implies S. So we can put those together and say if not Q, then S. Good. What do we do next? You only got to write one more thing.
QED.
QED. That's your like happy dance at the end of all of this. Which is what we were asked to show. Not Q implies S. That's the end of our proof. Now, can we simplify this a little? Probably. It's a perfectly valid proof. Right? There's no mistakes in here. But we wrote some things that we ended up not using. And we could make a shorter proof by getting rid of some of these things. But it's still a valid proof. But if we want to simplify it, did we use any of the conditional equivalents? I don't think so. So we can get rid of those. Don't do this on your homework, though. So we had to do the chain rule on 7 and 10. And 10 we had to do the chain rule on 2 and 3. So we needed 2 and 3, which got us to 10. And 7 we had to do the contrapositive on 1. And I don't think we used 8 or 9. So we had 3 hypotheses, 1, 2, 3, did the contrapositive on 1 to get 7, did the chain rule on 2 and 3 to get 10, and then did the chain rule on 7 and 10 to get 11. So we could rewrite this with 1, 2, 3, 4, 5, 6 steps. Again, it's still a valid proof. So we've shown that whatever the propositions P, Q, and R are, if we know that these 3 things are true, then this thing is true. And in this particular case, given these values of P, Q, and R, we've concluded that if I don't finish my homework, I'm going to wake up happy. Yay. So that's a typical example of a formal proof. And the things to note about this are, number one, we're only writing down things that we know are true. And that's either because they are hypotheses, right? This is basically a big if-then. If all of this, then that. So we're going to assume the hypothesis is true and try and prove the conclusion. So we can write down the hypotheses, those are true. Or we did things to things we knew were true and came up with other things that are true. For example, if P implies Q is true and P is true, we can say Q is true. And we can write down Q. So we're only writing down things that are true. We're numbering these, and we're writing the reason why each of these things is true. So that when somebody sees that we wrote this down, they don't have to think about, well, why is this true? They can say, oh, it's the chain rule of this with that. Right? So we're doing the thinking for the reader so that they don't have to figure this out. And then the last thing in the proof, the last thing that we show, is usually the thing that we are trying to demonstrate. In this case, not Q implies S. And then we kind of put a punctuation mark here at the end, which is QED, which is what we were asked to demonstrate. Or quite easily done, as my algebra teacher used to say. All right, does that make some sense? All right. So we can do all sorts of good stuff with this. So let's do some definitions. So a theorem is a statement that can be shown to be true. So we had a statement, if this and this and this, then that, right? Since we're able to show that it's true, we can call it a theorem. So this is a theorem if I go to sleep and then wake up hungry and all this kind of stuff, right? Then if I don't do my homework, I wake up happy. A proof is a demonstration that a theorem is true. That a theorem is a true statement. That's not worded well. Put it in your own words. Proof is how we show that something is a theorem. It's a demonstration that a statement is true. And there's usually two approaches we can take to proving something. So one is called a direct proof. We just did a direct proof. A direct proof, you write down things that are true, you apply laws of inference, and you eventually manage to write down the thing you're trying to show. Okay, that's what we just did. An indirect proof is basically proving the contrapositive of something. So for example, we want to prove that given P, Q is true. A direct proof, we would write down P, we'd do some other things, and eventually we can conclude Q. An indirect proof works like this. We start off by assuming not Q. And we logically argue from there, and eventually we prove not P. Okay, what we've done is we've done a direct proof of not Q implies not P. Well, this is logically equivalent to the contrapositive, which is if P, then Q. So So we can think of an indirect proof as a direct proof of the contrapositive of what we're after. But this is also sometimes called a proof by contradiction. And here's how we can think of this as contradiction. We're trying to prove if P then Q. Suppose Q is not true, right? That's what I'm stating here. And I go through all of this stuff. Well, if all of this follows, then eventually I show P is false. Okay, if Q is not true, I've proven that P is false. So if you tell me that P is true, Q has got to be true. Because if you tell me P is true and Q is false, I can show you that P is false. And that contradicts what you just said, which was that P was true. So indirect proof, proof by contradiction, basically the same thing. Formally, what we're doing is we're proving directly the contrapositive of your statement. But in practice, the mechanics of it feels like, okay, let's suppose the conclusion is false. Let's argue until we get a contradiction. The contradiction being P is false, but P is also true. All right, so let's do some other kinds of proofs. We're going to deal with integers, and I want to talk about even and odd integers. And we know intuitively what even and odd is. Even is divisible by 2 and odd isn't, right? But let me give you a more formal definition. So an integer, n, is even if we can write n equals 2 times k, where k is an integer. So an integer n is even if it can be written as twice some other integer. And an integer n is odd if we can write n equals 2k plus 1, where k is an integer. So why is 7 odd? Because we can write it as 2 times 3 plus 1. Why is 100 even? Because we can write it as 2 times 50. And so 0 is also even because it's 2 times 0. And negative 8 is even because it's 2 times negative 4. Right? So evens and odds alternate the way we expect. All right, so let me state a theorem. If n is odd, then n squared is odd. If n is an odd integer, then n squared is also an odd integer. We're always talking integers. Now, do we believe this theorem? How many people think it's true? Come on, don't be a skeptic. 5 squared is 25, that's odd. 1 squared is 1, that's odd. 3 squared is 9, that's odd. 11 squared is 121, that's odd. Negative 7 squared is 49, that's odd. Does it seem plausible?
It's true.
It's true. I call it a theorem, so unless I'm cheating, it's true. This is true. So let's prove it. And the only thing we have to prove it is this definition of even and odd and the rules of logic that we've covered so far in 3 classes of 215. So let's do a proof. Well, this is a proposition. If n is odd, then n squared is odd. This is also a proposition, n is odd. This is another proposition, n squared is odd. If this proposition, then that proposition, that's another proposition called a condition. Okay, how do we prove if P then Q? We're going to start off by assuming the hypothesis is true, and we're going to try to somehow show that the conclusion is true. So step 1, n is odd. Why is that true? It's just a hypothesis. N might not be odd, n might be 10. But if n is 10, I don't care, right? I'm going to say, let's assume n is odd, and I'm going to argue logically, and I'm going to try to come up with a statement that says n squared is odd. And then we'll be able to say, if this is true, then that is true. Okay, n is odd. Big deal. What can I say given the fact that n is odd? There's not a whole lot to choose from.
We'll give you the statement that if an integer is odd, then
I can use the definition of what it means to be odd. So since n is odd, there exists a k such that n equals 2 times k plus 1, where k is an integer. The reason for that is the definition of the word odd. So n is odd, that was an assumption, it was a hypothesis. But given that that's true, now I can state absolutely there is an integer k such that n equals 2 times k plus 1. Where do we go from here? Proofs are a little bit of an exercise in desperation sometimes, especially when we've only got, 5 lines of stuff written down. There's not a whole lot to choose from, right? So this is a good time to look at where we're trying to go. We're trying to get to a point where we can say n squared is odd. So what might we try to do for step 3? And it doesn't matter if it seems like it's going to get us to the answer. We're just kind of looking for something to do, so when our boss walks by, we look busy.
you could just write the hypothesis n squared is odd. That's a proposition.
Well, we can't write the proposition that we don't know is true, though.
You write n squared equals 2k plus n squared?
Yeah, let's square n, right? Why? I don't know, because it's something to do. Since n is equal to 2k plus 1, n squared equals 2k plus 1 squared. And let's go ahead and do some algebra and expand that. And that's definition, or that's statement 2 plus algebra. And we're allowed to use algebra because we believe algebra is true. Well, we've written n squared as 4k squared plus 4k plus 1. Does that get us closer to showing that n squared is odd? What does it mean to say n squared is odd? What's the definition of odd? It says we can write it as twice an integer plus 1. Can we write n squared as twice an integer plus 1? Algebra. What can we do with algebra?
He was asking what the word was.
Oh, algebra.
Can we make a substitution where we introduce a new variable? Is that equal to half of what the 4k squared plus 4k is? Is that a new variable to go with 2k squared plus 2k?
Okay. Let's do that. Let's take n squared, and instead of writing 4k squared plus 4k plus 1, let's write that as 2 times 2k squared plus 2k plus 1. Why? Algebra. We're assuming the reader understands algebra. This is absolutely true, right? This is 4k squared plus 4k plus 1. That's the same as this, which is n squared. But what did we just do? We just wrote n squared as 2 times something that looks like an integer plus 1. So I'm just going to go ahead and write an extra statement here and say 2k squared plus 2k is an integer. Why is that true? Well, because k is an integer, and we know that if we take an integer and we square it and we multiply by 2 and we add twice that integer, we're still going to get an integer. So I'm going to say properties of integers. And in reality, I'm not going to require that you make this extra step. I'm okay if from statement 4 you write down n squared is odd. Why? Because it's twice an integer plus 1. So this follows from 4 and 5 and definition of odd. And that's what we were asked to show. So there's a formal proof that the square of an odd number is odd. All right, so if you want something to work on at home, try to show that the square of an even number is even. And it's going to feel very similar to this. The goal with these proofs is not simply to come up with the conclusion. It's all about how you get there, right? We pretty much all would agree that the square of an even number is even if we think about it and try a few examples, right? The real question is, can you make a formal proof where each statement follows from what you've already written, and you can justify each statement, and at the end of your set of statements, you've got the conclusion you were after. All right. I will hopefully see you next week, sooner rather than later. Check out the website, check out your rave alerts. Have a great weekend, and I will see you next time.